Hi everyone, welcome to this particular session on chemical vapor deposition. So in your previous lectures you might have seen the different microfabrication techniques that are used for achieving a specific pattern or to produce a specific sensor or a device. So talking from the microfabrication perspective, there are three main techniques that are used to realize a particular device or a particular sensor that you are trying to fabricate. So the three main steps that are used in microfabrication techniques are as shown in the slide, that is lithography, then various thin film deposition techniques and etching methods. So lithography, as you all know, it is the art of transferring a pattern to a substrate, and the pattern can be based upon the device or the sensor that you are trying to fabricate. So you might have learned the basics of photolithography, where using a UV light, the pattern on a mask is transferred to a resist coated substrate. Then you have various thin film deposition techniques that are used to deposit thin films of various materials like metals or dielectrics. You have learned about physical vapor deposition, and also you might have heard about the term CVD, which stands for chemical vapor deposition. So using this thin film deposition, various thin films, as I mentioned, they are deposited on the substrate. Then you have different etching techniques. That means it includes wet etching, dry etching techniques by which already deposited thin film using either physical vapor deposition or chemical vapor deposition, these films are patterned, or the unnecessary films that are lying at desired locations on the substrate, they are removed using various etchants. It can be using a dry etching technique, or you can use a solution based etching where you are using some wet etchants to remove the material which are lying at the undesired locations. So in this particular session we will talk in details of thin film deposition techniques. So mainly when you talk about a thin film, it refers to films that are having thickness less than 1000 nanometers. And obviously due to this geometrical construction, there are different properties. The thin films are having very different properties from the compared to that of a bulk material due to the unique properties that arises from the dimensions and geometry limitations. And to have or to realize a thin film above your substrate, you can either go for a physical vapor deposition mechanism or a chemical vapor deposition mechanism. So as we mentioned, the major thin film deposition mechanisms are physical vapor deposition and chemical vapor deposition. So as the term suggests, in physical vapor deposition, there are no chemical reactions involved in that particular process. So you have learned physical vapor deposition is of different types like evaporation and sputtering, and again evaporation techniques are classified into thermal evaporation or E-beam evaporation, where different based upon the method that is used to evaporate the source material, the techniques are classified into thermal evaporation or E-beam evaporation. Here the constituent materials, they are evaporated using either thermal energy or an electron beam, and this vapors are they travel towards a substrate where you have placed your silicon wafer or whatever be the substrate where you are planning to have a thin film deposited. This substrates are placed inside a chamber, and these vapors travel and get condensed on the wafer surface, leading to the formation of a thin film. As we mentioned, it can be of evaporation method or sputtering technique. But coming to chemical vapor deposition method, as the name suggests, there are some sort of chemical reactions taking place in the chamber. For example, in a chemical vapor deposition technique, the reactant gases which are required to realize a particular thin film on a substrate, they are introduced into the chamber, and then various types of chemical reactions takes place on the surface of your wafer, and as a result a thin film will be formed above your wafer surface. So again, chemical vapor deposition technique is classified into different types based upon various conditions maintained inside that chamber where the CVD reactions happen, like APCVD, which stands for atmospheric pressure chemical vapor deposition. Then we have low pressure CVD, that is short form is LPCVD, and then we have plasma enhanced chemical vapor deposition, where instead of thermal energy, plasma is used to initiate a particular reaction to happen in the chamber. Then other than this mentioned physical vapor deposition and chemical vapor deposition techniques, there are various other methods that are gaining importance in ULSI fabrication. First one is a spin on glass technique where a liquid is coated upon a substrate and then later on it is heated so that a solid layer is formed. Then also you have electro deposition, which is you might all be familiar with this technique, that is electrolysis method, where we will be having a solution which has that particular ions of the species to be deposited. For example of the copper electroplating to form the global interconnects. So this is the basic principle of electrolysis technique which you all might be knowing. Then we have learned about thermal oxidation as well, where how a certain, for example, if you are talking about silicon dioxide formation above a silicon wafer, how thermal oxidation reactor chamber looks like, how the process proceeds further, consuming a certain amount of the substrate to realize a particular layer of silicon dioxide. So these are few other techniques that are used for realization of a thin film above a substrate. So moving on to why or what is the need of chemical vapor deposition compared to various physical vapor deposition techniques. So the first figure shows the main problem that is encountered with the physical vapor deposition technique, that is the process is known as, or the issue is known as geometrical shadowing. For example, if you have your wafer and you are having a step like profile above your wafer. Step like profile means if this is your particular wafer and you are having a step like profile already present on your wafer and you are planning to realize a thin film of material above this particular step like profile. So in such a case, in both evaporation and sputtering, we have a directional flux of the molecules that travels towards the wafer surface, eventually getting deposited on the wafer surface. But due to this directional flux of atoms, what happens is you won't be having a uniform coverage of film above the horizontal surface as well as along the side walls. So if this is a particular horizontal dimension and this is the particular vertical dimension, or it is what you meant by covering of the side walls of a step like profile. So when you look into a step like profile existing on your wafer surface, due to this particular directional flux in evaporation and sputtering, these side walls will not be covered uniformly, and that process we call it as geometrical shadowing. So when you are concerned about a contact where you want to place where you want to take electrical contact from your substrate, due to this unequal coverage of the thin film in the horizontal direction as well as in the vertical direction, the deposited layer will not be conformal, or in other words you can say that the layer that is formed above your substrate is non-conformal. That means the thickness of the layer deposited in the horizontal direction as well as the thickness of the layer that is deposited along the side walls or in the vertical direction will not be the same, and in such a situation we call the deposited layer as a non-conformal layer. So this is the main issue with the physical vapor deposition technique, and there are few steps or few techniques you can adopt to minimize this step coverage issue. First one is you can rotate as well as you can tilt your substrate during the physical vapor deposition mechanism. So if the substrate is, while the deposition process is happening, if you are continuously rotating the substrate or tilting it at a certain angle, this may help to have a uniform step coverage, or it may help to have equal deposition among the side wall as well. Also you can raise the substrate temperature as well. So what is the main reason why which or due to which what happens when you raise a substrate temperature is that when you, after depositing a thin film, when the substrate temperature is raised, it will result in enhanced surface diffusion, as well as when the substrate is rotated, it will minimize this shadowing effect. So these are a few techniques that can be used to minimize this step coverage concern. Also you can use a deposition source that covers a larger area. So even though you are planning to, or if you adopt, even if you adopt these techniques in your chamber, you cannot solve the step coverage issue to the maximum extent, or you cannot have a uniform step coverage whatever be the techniques you adopt in a physical vapor deposition chamber. Because if you are talking about a structure where the aspect ratio is greater than 1, for example, if you have a deep trench like this, a deep trench where the dimension in the vertical direction is more than that of the dimension in the horizontal direction, such a structure or geometry you call it as a structure with aspect ratio greater than 1. So, in a structure with a high aspect ratio, even if you rotate or tilt your substrate, or even if you increase the temperature so that the atoms have sufficient temperature to diffuse and align among themselves, or even if you use a large deposition source, still the coverage of the film deposited in the structure with a high aspect ratio will not be the same. So, in such a situation, that is the main drawback of a physical vapor deposition mechanism, and in such a situation we prefer to go to the technique which I have already mentioned, that is a chemical vapor deposition technique. So, the main advantage of a chemical vapor deposition technique compared to a PVD technique is that chemical vapor deposition is more conformal than PVD. That means the thickness of the layer deposited above a particular a step like profile, for example existing in your wafer, in that the thickness of the layer deposited in the horizontal direction will be the same for the thickness along the vertical dimension as well. And the figure in this particular slide shows a 100% conformal deposition. That means the layer deposited is uniform throughout the surface of your substrate. So, again the next slide shows the example of a conformal deposition and a non-conformal deposition. So, by looking at how the layer is formed, for example the black structure shows the geometry existing in your wafer surface, and the red layer shows the layer that is deposited above your substrate. So, you looking into the figure, you can say the first figure is a conformal deposition. It is because the thickness is the same in the horizontal dimension as well as in the vertical dimension. But looking at the second figure, you can say directly that it is a non-conformal deposition. That means the thickness of the layer here, in both the horizontal dimension the thickness is the same, but coming to the side walls or in the vertical dimension the thickness is not the same. So, the first figure is a conformal deposition, whereas the second figure is a non-conformal deposition. But you can think of a situation where you wish to have a non-conformal deposition. So, I hope you might have heard of the term lift-off. So, what happens in lift-off compared to a conventional lithography technique is that you will be depositing, for example, if you have a wafer, then you will be depositing or you will be spin coating, the right term is spin coat, you will be spin coating photoresist above your wafer. So, this is a lift-off technique that I am trying to explain. So, in lift-off you will be having your wafer, you will deposit your photoresist, you will spin coat your photoresist, and you will, but for example you are getting a patterned photoresist in this particular manner, where this is the photoresist which is abbreviated as PR. So, this is the photoresist patterned above your silicon wafer. And now using any of the thin film deposition technique, for example say you are using any of the physical vapor deposition technique, either it is evaporation or sputtering. So, after this thin film deposition technique, in your wafer where you have already patterned or spin coated your photoresist, the thin film deposition, the layer deposited will be of this particular manner, because in PVD as we mentioned, the thickness of the thin film that is deposited above your structure in the horizontal direction will not be the same in the vertical direction as well. So, you can say almost the thin film that is deposited above your resist coated wafer would look like this. And now when you dip this entire structure in acetone, so acetone as we all know, it is used for stripping photoresist or it is used for removing photoresist above your wafer. So, when this entire structure is dipped in acetone, what happens is the photoresist layer will be removed. So, this particular photoresist and this particular photoresist layers will be removed, and when this photoresist get dissolved in acetone, it removes off the thin film that is deposited above your PR layer. So, after the acetone dip technique, acetone dip step, the pattern that will be existing above your wafer will be, you will have a thin film of metal or whatever material above your wafer directly. This is a thin film existing above your wafer. It is because acetone has dissolved your photoresist, therefore the metal layer above the patterned photoresist will also be removed. So, this is just the thin film that is existing above your wafer. So, when you think of a situation or when you think of an application, when you are using a lift-off technique, you would always prefer to have a non-conformal deposition, because if the deposition of the thin film was conformal, then what happens is the layer will be covering the entire side walls as well. So, the thin film deposited would cover the side walls as well as the horizontal dimension. So, when you think of putting this entire structure in acetone for removing the photoresist, what happens is the photoresist, this particular location and this particular location, the photoresist will be dissolved, but since there is a metal coating along the side walls as well, you will not be able to get a perfect thin film structure as shown in the figure below, because there is a thin film metal deposited along the vertical side walls as well. But if you are intending or if you are planning to have a lift-off technique in your entire process flow, it is always desired to have a non-conformal deposition. But if you are planning to have a normal lithography and patterning techniques, you would always prefer to have a conformal deposition. So, the entire catch point from this particular slide is that depending upon your process flow, that is, for example, if you are planning to fabricate a sensor or a particular device, you will first of all set the entire process flow that is required to realize your particular device, and based on that process flow, whether you are adopting a lift-off technique or you are adopting a normal lithography and thin film deposition technique, the choice of the deposition techniques would vary. If there is a lift-off process in your process flow, you would prefer to have a non-conformal deposition of the thin film so that it is more or less easy to remove that particular layer. And if there is a normal lithography and a normal process flow, normal in the sense it is not a kind of lift-off technique, in such a process you would like to have a conformal deposition, and in that case you would prefer to have chemical vapor deposition as the thin film deposition mechanism adopted. So, the figure below also shows another example for a conformal and non-conformal deposition. So, this particular figure A, it is a conformal deposition because throughout you have a uniform thickness of the metal film that is deposited above your wafer, which is having a particular geometry. And in the figure B, you can see the thin film deposition thickness is different along the vertical dimension. So, that is obviously a non-conformal deposition. Okay, so moving on to the basics of chemical vapor deposition technique. As we mentioned, CVD can provide better uniformity than a physical vapor deposition technique. So, wherever uniformity is a critical condition, we always prefer to choose CVD as the thin film deposition mechanism. So, as the name suggests, there are some sort of chemical reactions happening within the chamber. So, the precursor molecules are chosen depending upon the thin film that you would like to realize above your wafer surface. So, the precursor molecules, it can be either in the gaseous form so that it can be directly taken inside your chamber where your substrates are aligned, or the precursors can be in a liquid form. For example, it can be taken in a bubbler and you can evaporate it so that the vapor molecules can be taken to the chamber and reacted with your substrate to form a thin film. So, whenever you are using a liquid source as your precursor molecule, you have to use an inert gas like nitrogen or argon that would act as a carrier gas. Carrier gas in the sense that is used to take your vapor molecules from the bubbler to the chamber. So, the purpose of using an inert gas is that it should not react with your substrate at any cost, but at the same time the precursor molecules which are evaporated from the liquid source in the bubbler should be taken appropriately to the chamber where you have your substrate placed for the reaction to happen. Then CVD can be used to deposit different metals or different dielectric materials, and basically there are two types of reactions that is happening in a chemical vapor deposition process, that is a homogeneous or gas phase reaction and heterogeneous or a solid surface reaction. So, homogeneous reactions means this particular reactions happen in the gas phase, and as a result the byproducts that are formed will get deposited on your wafer. So, actually the reaction is not happening on your wafer surface, but in turn it happens in the gas phase, and only the byproducts will get deposited above your wafer surface. So, if homogeneous reactions are happening more in your reaction chamber, you can say that the deposited layer would be of poor uniformity or it will not be of that good quality, because only the byproducts they are landing on your wafer, leading to a non-uniformity in the deposited layer. In the other case, you can have a heterogeneous or solid surface reaction, and that is the type of reaction that is preferred in a CVD chamber, because in this particular type of heterogeneous reaction, the actual chemical reactions are happening on the wafer surface itself, and a solid film is deposited or formed on the wafer. So, compared to homogeneous reaction, a CVD chamber where heterogeneous reactions happens more, you can say that the quality of the deposited film will be more better and the layer formed will be more uniform as well. So, always in a CVD chamber, the partial pressure of the reactant molecules are adjusted in such a way that always heterogeneous reactions are preferred. So, the figure shows the basic steps of a chemical vapor deposition process. So, the first step is, so this is the first step. In the first step, as I mentioned, you will have a chamber. For example, in the figure below you can see there is a chamber. You will have a chamber where you will have a substrate holder, and you can arrange your substrates in the manner as required, and you will have a inlet where the precursor molecules are taken to the inside of the reactor, and chemical reactions takes place in your chamber, and a layer of film will be deposited or formed on your wafer surface, and after the particular chemical reaction, whatever be the byproducts generated, it will be taken outside of the chamber. This is the entire overview of a chemical vapor deposition process. So, the first step, as I mentioned, would be the reactants will be transported to the chamber where the deposition process takes place by means of a forced convection, because you are using some sort of pump or some forceful mechanism to take your precursor molecules to your chamber, and that is why you term that process as a forced convection mechanism. So, the reactant molecules are taken inside your chamber. Then once these reactant molecules enter your chamber, you can say that at the inlet of the chamber, the concentration of the precursor molecules will be high compared to the areas compared to other areas of your chamber. So, due to this difference in concentration, the reactants will be diffused from the mainstream to the place where you have kept your wafer. It is due to the diffusion mechanism, the reactant molecules enter the chamber and get that is, it gets attracted to the place where you have kept your wafer above your substrate holder, and some sort of chemical reaction starts to happen, and this process is due to the diffusion mechanism due to a concentration gradient. And once this reactant or precursor molecules reaches your wafer surface, adsorption happens. All the precursor molecules will be adsorbed onto your wafer surface, and as a result different types of chemical reactions happens, like thermal decomposition or some sort of pyrolysis reaction or a reduction mechanism. So, depending upon the temperature in the chamber, the pressure in the chamber, what is the type of precursor molecules that you have chosen. So, depending on all these steps, the certain set of chemical reactions would happen on your wafer surface, and a few byproducts will be produced that will be later on desorbed from the surface of your wafer, and again due to the concentration difference of the byproduct at places near to your wafer and at regions away from your chamber, again due to this concentration difference, this byproducts will be taken or moved away from your substrate surface, and finally again by means of a forced convection mechanism, this byproducts will be taken away from the deposition chamber. So, this particular figure also shows the steps that I just briefed now, like there is an influx of precursor molecules to the reaction chamber, then there is a transport due to the diffusion mechanism. These molecules will be transported to your wafer surface where it will be adsorbed, and various types of chemical reactions takes place on the surface of your wafer, which we will see in the upcoming slides. And finally, the byproducts will be desorbed from your wafer surface, and it will be taken out of the chamber where the reaction happens, again through a forced convection mechanism. And the figure below, this particular figure, it shows the basic, just a schematic of how a CVD reactor would look like. You have a quartz tube that is shown in the black color, where you have a substrate holder and all your substrates are arranged in a vertical direction. So, the number of substrates, how the substrates in the sense the number of wafers, how the wafers are stacked inside your chamber, everything depends upon the type of the CVD mechanism. Then there are heating coils to heat the chamber to a high temperature at which a particular reaction happens, and then this is the point at which the precursor molecules are taken inside the chamber, and at the other end you have an outlet so that the byproducts are taken outside the reaction chamber. So, moving on to when you are designing a particular chamber, what are the basic steps that you should take into consideration? That is, what type of source should be used in a CVD chamber. So, the type of source chosen can be either gas, that is the easiest type of source because you can directly take this precursor gaseous molecules to the chamber where the reaction happens. Also, the source can be in the form of a volatile liquid, so that the liquid evaporates, or it can be taken in a bubbler, it evaporates, and using a carrier gas this vapor can be taken to your chamber. Also, you can use a solid which are sublimable in nature, so that it can be directly converted to the vapor form and the vapors can be taken for the reaction. Or you can use a source that is a combination of either a gaseous form or in a liquid form or in a solid form. Then whatever be the type of source material that you are using, it should be sufficiently stable at the temperature at which the particular reaction happens, and the source should be sufficiently volatile in nature. And as we mentioned in the first slide, the partial pressure in the chamber should be such that heterogeneous reactions are favored, as well as even though heterogeneous reactions takes place, we should be able to have a good growth rate inside the CVD chamber. So, the choice of the source material should be such that it favors good growth rate at the particular partial pressure at which the reaction chamber is maintained. Then the temperature at which the particular reaction happens, it should be always less than the melting point of the substrate that you have chosen. Then whatever be the byproducts that is formed after the particular chemical reaction, it should be easily removable. And the toxicity nature of the source material should also be as less as possible, and the type of substrate that is chosen is also important, because for example tungsten hexafluoride, this particular film can be easily formed on a silicon substrate, but it is difficult to form that particular film on a SiO2 substrate. So, the type of the substrate that is chosen in a particular CVD process also matters. So, we will end this particular session by this particular slide, and we will continue with the remaining portions in the next class. Thank you.